Alrighty. Thank you, Paul, and thank you everyone there for your hospitality this evening. I'm going to be talking about new tools for STEM, cyber, and makers. I have too many slides, so what I'm going to do is just kind of hit briefly on these topics on the front and really focus on the code examples. But we'll breeze through some of these. Motivation, I was looking to see, can we run Java software directly on the hardware? And that seems relevant from a defensive cyber standpoint. We'll talk about that here in a second. But basically with STEM and cyber and makers, I think they all have a similar requirement to be able to experiment with hardware and software running together. And this proof of concept, I think, demonstrates that it's certainly this proof of concept, it's just that, but it does have some advantages over C and Unix in that we can greatly reduce the number of lines running on the hardware and then bring some stronger typing. So the embedded hardware that I'm running with, it's a single board computer, BeagleBone Black. You may have seen them on like Sparkman, Adafruit. Currently this code is running with the UART, dual mode timer, interrupt controller, a GPIO, and the power reset. I haven't even started to work at all with the real-time unit or DMA or any of these other interfaces down here. So there's a lot more that can be done. And so in the demo here, or the slides anyway, I'm running the MacBook with a USB to TTL. And so just the way this code runs, U-boot emits this starting application, and then this start line here is the first text from the Java code. It sits and waits for you to hit the G or go. That starts the timer and basically blinks the LED, moves down the line from left top to bottom here. You can enter the TD or timer disable command, hit a few returns here just to kind of see the hello prompt come back. And all these screens are just one continuation from the other. So here I'm just LED 2 clear. And so then you notice that all the LEDs are clear. And so all this code run here started as Java source code. The next command, LED 4 set, and that turns on the fourth LED, and you get this little artifact up here. It's a little easier to see that it is one LED. Also in this code, we won't really look at any of the implementation here, but there is I did implement a very simple console port debugger that allows me to set breakpoints. I'm generating all the assembly that's running, and so I go ahead and put some no-ops in there, beginning and ending of methods and that sort of thing, just so that the little debugger doesn't have to know about storing breakpoints or anything like that. It just, whenever it executes one, it breaks, or I'm sorry, when you're trying to set one, it doesn't have to worry about keeping up with the real instruction. But anyway, with the debugger, you can display registers, memory contents, call stack, and the method variables for stack frame. So I did in between the previous screen and this screen, I did a power reset command that does a warm reset on the board. A U-boot comes back up. I set a breakpoint in this series summation routine when it's a recursive routine. It's a way to test your stack, the way how you're managing your memory and your stack. So I set the breakpoint here in, oops, sorry. Then I hit go, and then it just goes ahead and executes like it did before, and that's because we haven't run anything with the stack. So I'll do the timer disable here, and then it stops the interrupts. And I run this little stack test with a n of 2, and it's hit go. And then we see here, we hit the breakpoint where we set the breakpoint, the address for the breakpoint. And we go ahead and hit go there, and we get the series summation, 2 + 1 is 3. So picking up from the previous, I'm sorry, did somebody have a question, or I got some feedback on this end?
Yeah, I think you're okay. We'll yell and holler at you.
Okay. And so after the stack test of 2, I did a stack test of 3. Return, we hit the breakpoint. And then from that point, I just list the stack frames that are current. And so at that point, we have, how many frames do we have here? 1, 2, 3, 4, 5 different frames. Method 0 is the one that's current. There's 2 local variables in that method, and this is the return address. Here's method 1 called method 0. Method 1 has 2 local variables and the return address and so on. This is a continuation in the previous column, displaying the registers, and then after that, listing the variables within the method 0. That method has 2 local variables. The first one is actually the parameter that was passed in, and that's a value. We can see here that's a value of 1. This second variable with the index 1 really hasn't been assigned yet, so that's not really a valid number. But anyway, so you can just kind of see some of the capabilities of the debugger there. And so talking about the caveats of what's implemented here, it's just a proof of concept, but it does illustrate some essential capabilities if you're going to try to run, if you're trying to prove to yourself whether Java can run directly on the hardware or not. We're doing memory access, memory allocation, and constraints as far as are you overrunning the stack or overrunning the heap, and we're processing interrupts. Of course, the execution environment is not a compliant JVM, it's just a proof of concept. Only executes statically linked code, a very small subset of the Java language features, static classes, static methods, static primitive fields, only int and boolean. It does do dynamic allocation of character arrays, but there's no memory, no garbage collection or anything like that. We'll see, I'm using a lot of custom annotations to implement this in just a limited amount of native assembly source language files. So right now there's no objects, exceptions, or threads. And I haven't created a Java platform, I'm just compiling against local code in the project. I am working from the Java 8 spec for the language and the virtual machine. This is a list of the VM instructions that I've implemented to various degrees depending on which instruction you're talking about. This is a list of ones that I have no implementation for. You know, doubles, floats, anything related to those. Of course, anything related to objects, invoke special or virtual, no switch statements or synchronization or anything like that. So the way I got started with this cross-platform tool chain was I followed I started trying to build the Minix ARM port for BeagleBone Black, and from that I got a version of U-Boot and the GNU bin utils, the assembler, the linker, object copy, and object dump. Now that I'm got my tool chain. I'm running from NetBeans. I've got everything in one project right now. Am I talking too loudly, or is that kind of appropriate?
You're real good. I think everybody
Okay.
is working really well.
Thanks. So after doing the IDE build, I run the native generation tool. It's dependent on the BCEL library and velocity. That generates the ARM assembly. And then from there, I'm running a build script that does the assembling, linking, and copy and dump. So I'm using this object dump just so I can get my addresses for the debugger. This is a notional workflow, notional diagram of the workflow that's running with the native generation tool. For each of the Java classes that I'm generating code, I grab the information out with the BCL, then I take the template and generate the assembly files. So this is the package structure that I'm using in my project. Basically, these are some placeholders here for like Stack Overflow, out of memory error. The Hello World example is in here. This middle section is code that maybe supports native generation, maybe supports the code running on the target. And then I've got the native gen packages here. And down here, the system on the chip modules, the GPIO, interrupt controller, power, timer, and UART. And so we'll start looking at how is all this implemented. We'll look at the main memory allocation, one of the modules on the system on the chip, the interrupt controller. And so it's a little bit, we'll be looking at code that's running on the target, and we'll also be looking at the templates that are used to generate that code, or generate the executable code anyway. So this is a code segment from the Java main. It looks like typical Java source code. We're declaring a character array for our little prompt that we saw on the previous slides. Down here, we get into initializing some of the subsystems. We're going to disable the watchdog timer so we can interact with the board and stuff. Initialize the GPIO, the timer, interrupt controller, and the dual mode timer while we start it here. This is pretty much the main loop. Basically, it just sits and reads characters that are typed in from the Mac or from the host computer here. It reads those off the UART, puts them in this character array, and then when it detects a carriage return, since we don't have objects, we just pass that same command line essentially to each one of the different subsystems, and let the subsystem decide if there's anything for it to do. Is it a GPIO command, meaning is it one of the LED set or clear commands? Is it timer disable or timer enable? Is it a power reset? And then these two, the heap manager, you can run a heap overflow test, and the stack manager, you can run a stack overflow test and that stack test routine that we looked at. The idea being to be able to give someone we don't want to have them overriding their memory. So if we look at how we generated the executable code for the memory allocation, this is the line from the main where we declare the character array. And for the allocation of this array, we're getting the JVM instructions byte immediate push and then a new array VM instruction. So depending on what the context is, we have a template for every JVM instruction, and we merge that with whatever the relevant data is to generate the assembly code. And so the new array, this is where we see using the BCL visitor pattern. When I come to a new array, I'm going to pull up, I'm going to add this, set this variable, and that will be inserted and then inserted into the assembly code that's written out in this merge, writing to this file writer. And so what we see here is this is a branch and link to this class. Essentially, it ends up being this class and method. And so what we're doing is we're implementing the allocation of memory. We're implementing it in Java that's running on the board, which I think is interesting. And so it's the way this is currently implemented, the way the array is implemented, it's writing the length of the array as the first address of the array so that the Java code can make sure that it's not overrunning the bounds of the array. So then if we look at the interrupt controller, what code is driving the interrupt controller? We saw over in the hello world main, interrupt controller initialize. And so down here we see, it looks just like normal Java code: enable, priority, threshold mechanism, set timer to interrupt priority. And this is where we start to see some different, we're doing device memory write int. And we'll look at that on the next slide. So the class device memory, read int and write int, there's no Java code there. It's just an annotation for whole method generation. And that's a custom annotation defined here in the project. So this is an example of where instead of generating, instead of using templates for individual JVM instructions, we're just using the template for the entire method. There's very limited number of these in this project, but it was the only way that I could see to get this to run. Some of the, I haven't started working with Java 9 yet, but of course the idea would be very few people, really the only people that would be writing this kind of code would be writing, the ones developing the execution environment. Application developers or people that just wanted to interact with the subsystems wouldn't be using this kind of code. And so in the native generation tool, there's a class generate instructions, and for each method that's being generated, it takes a look to see what annotations are associated with that method. And then if it is a whole method generation, then it's going to call this method, basically using, just using the method name here to find the template and then just merge that template with the current data and generate our output. We'll take a look at that on the next slide. So this is the write int method. We saw it 2 slides back here. Setting up the stack frame and that sort of thing, that's in a different template, that's in pre-method. This is the bulk of the write int. You notice I'm using these, even here I'm using these template variables, basically so if I want to change my register convention, I can do that, and I don't have to come back and re-wicker these manually generated assembly files. And this is just essentially popping the stat frame. And so then as far as how do we process interrupts, in the startup routine, the one that's started by U-boot, we take the vector table base address and write that to the ARM vector base address register. We have another file, I call it, it's just where all the exception handlers are. ARM, you know, things like reset, undefined instruction, ARM calls all those exceptions. And so when one of these exceptions occurs, the handler address is loaded up into the program counter, and then it just jumps off to that handler. So, for example, when an interrupt happens, that's this exception 7, or yes, exception 7, and we'll look at that on the next slide. So we have a kind of a template here, and the thing we're focusing on as far as integrating with Java is we've got this branch and link to a class name and an interrupt Java handler, but these are just variables so that we don't have to put the actual Java class name or the Java method name in here. We'll take a look at how we're mapping those together in the next slide. The embedded source code is going to use this custom annotation ARM exception handlers, and you can define which method you want to be your reset handler all the way down to your interrupt handler. During the code generation time, if you're going to install your interrupt handlers, well, I guess this method is just called. And if that annotation is present, then it'll go ahead and emit the assembly code for that. So this file, interrupt handlers, is the Java code that processes these interrupts. It has this annotation where it's essentially doing this mapping between method names to labels in the annotation. So the method here is interrupt handler. You know, it just goes and reads the interrupt controller, sees what's the active interrupt request. If it's the timer 2, then we'll print out that pre-message, the little lowercase int, the timer message being the uppercase timer, end of line, advance the LED, clear the pending event on the timer, acknowledge the interrupt request, and then everything will just return back in a normal flow. So here we're going to look at, well, how did I implement the heap memory bounds checking? So in the context of allocating even the character array, we'll ultimately call this allocate bytes and pass in how many bytes do you want to allocate, and then do a test and see, well, does that exceed the heap end address? And if so, throw a new out of memory error. Well, the throw and the new, those are very immature kind of proof of concept implementations. But this heap end address is something I think we can look at here. We'll take a look at that on the next slide. So this LL main, this is the file that's started by U-boot. Currently I'm statically defining the heap in there, and I define the label heap max address. We'll see that on the next slide. And also to implement this, I'm defining this custom annotation, JM final static int field. So then when we take a look in the declarations of the heap manager, we have the heap end address, and we decorate it with this custom annotation. And here's where we provide the label from the assembly file that we were just looking at. And so because this static int needs an initialization, that happens at class initialization time. I'm generating assembly code for that as well. The difference here is we really don't want this value. We want the value that we're defining in this annotation. So for the put static, I have a custom put static for cases where it's decorated with this field, and I'm dropping this value and instead using this value, the address of this label. And so I am working towards a Kickstarter campaign in June. This is a very early proof of concept, but yet I think it's interesting from potentially various communities, whether you're doing STEM or you're a maker and you want to interact with hardware, or if you're cyber and you want to look at, well, how are different ways that I can run code directly on hardware? So I was going to release this as open source and write a book, basically laying out all the steps for how you could do this, detailed design and just description of the design and implementation. Ideally also generate Java versions of the assembler, the linker, some of these other utilities. That's seems to be one of the barriers of entry of writing code directly for hardware, is getting your cross-platform tool chain all set up. And so I know that was really quick to go through. I don't know if anybody has any questions or wanted to go back and look at anything else a second time.
Thank you, Jeff. I think we do have a question. I'll try and facilitate.
I'm sorry, I couldn't hear the
You have to come
question.
forward. Yeah. The mic is in the camera.
Oh.
There we go.
Is there a way to embed an assembly code as part of the Java source code and have it compiled directly into the assembly code?
Yes, I'm sorry. I understand. Currently, no, there's no way to put it directly in the Java source code.
We have the flying camera. Who's next? Maybe, do you have the device with you that you could just show it off?
Oh, it's upstairs, and I would hate to try to get it now. It's
Okay, no worries. How about when you talk about your code, give us some examples of the applications.
Well, that's a great question. I think one of the things I need to do as part of this Kickstarter campaign is I want to start a dialogue. Spark Fun has some education people, and I wanted to get with them and get some ideas about little projects that I could set up illustrating what you can do with this. You know, we looked at, there's just a ton of interfaces on this particular little board. And, you know, I got this board in like August of last year. And so I haven't had the time to start exploring some of those other ideas. But, you know, anything that you can think of, you know, it's just this, as far as like the general purpose input output, I think there's, gosh, over, I want to say, what, 128 lines that if you set up all the configuration, you can't get all those out at one time, but it's really, this is an amazing little board. You could do a lot with it. I just haven't gotten to that point yet.
Okay. Yeah, so this is the question was how is this program related to cybersecurity?
Right. So part of the objective was to say with Linux is a huge code base, and C, I think really you're passing a lot of pointers around throughout the code base, and the objective here is a more defensive posture towards cybersecurity. And one possible way of implementing that is to really reduce the number of lines of code that you have running on your hardware. And so in this kind of scenario, it's basically just trying to say, well, how can I move my application as close to the hardware as possible and eliminate as much of the intermediate software as I can so that I get down to a very small code base. So it's really more, how can I get to a more defensive posture with a newer language? So many of the vulnerabilities are buffer overflows, and ideally you would be able to eliminate those by moving to a more strongly typed language.
Okay, is that good, Kevin? Okay. Okay.
I guess one thing I wanted to add, I haven't started working with Java 9 yet, but to me that almost seems to be that that's one of the objectives of Java 9. That's one reason I'm really interested in the next session is, what capability does Java 9 give you to really slice and dice and pare down how much of the platform you include in your system. I don't know if you'll be hitting on that, Paul, or not.
Almost a good segue, but probably not. So yeah, thank you. Was there another question in the back corner over here? Or? No, Steve, okay. Say again? How much memory is on the board itself? What's the capability that you're trying to push Java into?
Let's see, the flash is like 4 gig and the RAM is 512 meg. So there's actually a lot of room there. You saw in some of my little example assembly, the demo, the code that I was running for those demo slides was using a 2K stack, a 2K heap, and I'm kind of playing around with the idea of having, for a single thread, have essentially one stack for the application and then one stack for exception processing. That was one of the things I ran into when I tried to do the Stack Overflow constraint. When I was, I'm not doing any real exception processing. I just, when I identify the Stack Overflow, I just spit out some text to let you know that the application tried to overflow the stack, and then I just go into essentially a busy wait. But one of the problems I ran into was when I ran my Stack Overflow test, and then I tried to do that little bit of spitting out some text I/O, my overflow check kept preventing me from doing anything. And so then I said, well, maybe, I don't know how a compliant JVM does it, but I said, well, maybe I'll just use a different stack to do the exception processing. I don't know if I'm making any sense or not.
A little bit. Go ahead, Kevin.
Jeff, when you're looking at these maker boards, did you look at ARM processors that support trust zone or trusted execution environment capability? So there are IoT makers that are specifically using ARM chip and have trust zone, so they can go into hardware and software isolation. Have you looked at all into that topic?
I'm sorry, I only caught a few words there. It sounded like you were talking about trust zones being implemented or being available on the chip itself.
Yeah, ARM owns the patents for trust zone. So many of the chip manufacturers like Qualcomm, NVIDIA, TI, etc., license this. So they build inside of the chip essentially what's called a secure world. The marketing label is trust zone, but they're going out to the IoT market and say, hey, buy a chip that has trusted execution capabilities. So now you can isolate, have a separate VM that can't, if it's infected, it cannot infect other VMs that are running inside of the secure world. So it's one thing to have code that's better than C, for various reasons, but what you want a combination of is a language plus an isolation capability to segment the memory and have protected memory so nothing can get in there. Even if they broke into the operating system, they can't get inside of these trusted execution environments. And again, it's an ARM technology.
I appreciate that. That was not that specific capability, but that's one of the longer term objectives is, with when you have complete control over this code base, it seems easier to port to new hardware capabilities. Things like this real-time unit, and also trusted zone.
Okay, great. Last question. All right, Jeff, I think we've got it.
Well, thank you all very much. I appreciate your feedback and your questions, and hope you all have a great night. And yeah, Paul, if I'll just go on mute here and maybe sit in with the rest of the session, if that's okay.
Yeah, that's fine. Let's have a big round of applause for Jeff. Thank you.
Thank you all.
Yeah, thanks for staying up late. And yes, the next segment will start in about 10 minutes. What time do we have? Yeah, let's start at 8 o'clock. That's like in 9 minutes. So a little bit more pizza, restroom breaks, and I'll get the stuff rejiggered up here. And if you